Hello, my dear students and the rest of the learners. Welcome to this presentation in which we are going to be discussing or learning about data representation in the computer. This is part one of a three-part series of presentations in this topic. The title of this presentation is Introduction to Data Representation. My name is Meme JM, or you can simply call me Emily Swap. In this presentation, we shall look at the concepts and reasons for data representation. Then we shall look at definition of terms that are used in data representation. Then we shall look at number systems and their representation of integral values. And our focus will be on the decimal, binary, octal, and hexadecimal. We shall also look at symbolic representation, with our focus being on BCD, EBCDIC, and ASCII. Let's now look at the concepts and the reasons for data representation. The way in which data is stored and represented in the computer depends on the medium of storing it and the type of data. The two types of data are discrete data and continuous data. Discrete data is the data that can be counted and has no value in between. In other words, this is data that does not have any fractions or any decimal points. For example, you cannot have 2.5 people. You can't have 2.5 people. While continuous data is data that can be measured and can be recorded at many different points. For example, 2.5 kilograms. In other words, continuous data is data that contains decimal places or fractional parts. Discrete data is also called digital data, while continuous data is also called analog data. Examples of continuous data are temperature, length, volume, amongst the others. And discrete data is processed by digital computers, while continuous data is processed by analog computers. However, hybrid computers process both digital and analog data. In digital computers, the user input is first converted and transmitted as electrical pulses that can be represented by two distinct digits, ones and zeros, which we normally call the binary digits or bits before processing. A computer consists of a number of two states or bistable devices that process and store the data. A bistable device is one which can be set to one of two states at any one time or at any one point in time. The binary number system, which consists of two digits, 0 and 1, is normally used by computers to represent the two states. These two binary digits are called bits. And therefore bit, or the term bit, is an acronym or a short form for binary digits. Data and instructions cannot be entered and processed directly into computers using human language. And for that reason, any data and instructions that are entered into the computer must first be converted from human readable form to binary form, or what we call the machine readable form, for processing to take place. Information is stored in the computer also in form of bits. The stored bits are usually retrieved from the computer's memory for manipulation by the microprocessor. In electric and electronic circuits, when the switch is closed or there is a high voltage, that is, the socket is on, this is represented as 1. While when the switch is open or there is low voltage or no voltage flow, that state is represented as a 0. When data also is recorded on a magnetic media, the presence of a magnetic field in one direction is represented as a 1, while the field in the opposite direction is represented as 0. On optical media, data is recorded and read from it using a laser beam of light. The parts that reflect light are called lines and are represented as 1, while those parts that absorb or don't reflect light are called pits and are represented as 0. A land can also be seen to be the presence of light, that is, or absence of light, or absence of pit. I repeat, a land can also be said to be the presence of light, that is, absence of pit, while a pit can be seen to be the absence of light, that is, presence of pit, very tiny holes. The computer system is made up of logic that works only with the 2 states, on and off. For computer to process information, the information itself must be represented in the 2 states that the computer can store and process. The on and off are represented as 1 and 0. So, some reasons as to why binary systems are used in computers and in other fields in digital technology include: number 1, devices designed using binary logic are simple, more reliable, and they consume less energy. Number 2, it's difficult to develop devices that can understand or process natural language directly due to the complexity of natural languages. Number 3, devices that read, process, and output data in digital form are used in the computers and in other digital devices. My dear students and the rest of the learners, that is why number systems or data representation in the computer is key, and you have seen the importance of binary digits, what we are calling the on and off, presence or absence of electricity or electrical signals, pits and lines, etc. Let's now look at some of the terms that we use when we are talking about or referring to data representation in computing. We commence with the term that I have already mentioned several times in this introductory section, which is bit. A bit, just as I have said, is a short form for binary, B for binary, digit, IT for digit, which can either be a 0 or a 1. It's the basic unit of data or information in digital computers. A nibble, on the other hand, is a group of 4 bits, which is normally a half of a byte. An example is 1, 1, 0, 0. These are 4 bits. And this series or this representation contains 1 ones, and that is 2 ones and 2 zeros. A byte is therefore a group of 8 bits used to present a character. An example is 1 1 0 0 0 0 0 1. This represents a character, which is in this case character A. My dear students and the rest of the learners, may I encourage you not to worry about how we arrive at these bits, because we are going to discuss in depth, and I will demonstrate and illustrate how we arrive at various numbers in my next presentations, which are data representation in the computer, part 2 of 3 and part 3 of 3. Therefore, make sure that you have visited the YouTube channel by the name MLSwap ICT to access the part 2 and the part 3 of presentations in this series, so that you can gain better understanding of the concepts in relation to data representation in the computers. A byte is considered as the basic unit of measuring memory size in computers. A word is a group of either 1 or more bytes and is the largest amount of memory that the computer can handle. My dear students and the rest of the learners, it is important to note that you can refer to a byte as a character, while a group of characters can form a word. So an example of a word is base. Base. Base is a word composed of 4 characters. Character B, character A, character S, character E. Or for those modern kings, we can say it is character B, character A, character S, and character A. Base. Let's look at each of these characters and its respective bits. Character B is represented in form of binary digit as 1 1 0 0 0 0 1 0. R is 1 1 0 0 0 0 01. Is bits 1, 1, 1, 0, 0, 0, 1, 0. E is 1, 1, 0, 0, 0, 1, 0, 1. The word base is therefore made up of 4 characters, which is equal to 4 bytes. Why? I have already said that a single byte is equals to a single character. And therefore, byte and character are one and the same thing. Byte. 1 byte is equals to 1 character. And therefore, 4 characters are equal to 4 bytes. And because each byte is composed of 8 bits, then the total number of bits that form the word base is equals to 8 bits times 4, which is equal to 2 bits. A word can therefore be said to be the number of adjacent bits that can be stored and manipulated as a unit. For example, the word base can be represented in form of bits as 1, 1, 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 0, 1. Those are a series of 2 bits organized based on their arrangement on the word base. Therefore, in the series of bits, we have the first 8 bits representing boo or B. The next sequence of 8 bits represent A, or the next sequence of 8 bits represent S, and the last series of 8 bits represent E. A word length is therefore the measure of the number of bits in each word. For example, the word length for the base, or the word length for the word base that we have already looked at is 2. And therefore, when we refer to word length, we are simply referring to the total number of bits, that represent the full word. Remember, in computing, even a space is a character, and therefore it also consists of 1 byte, which is equal to 8 bits. Complex data is represented using strings or streams of binary digits. A single bit can represent one of the 2 values, 1 and 0. A group of 2 bits can be used to represent 1 of 4, which is, of course, 2 representing the number 2, then raised to 2, values. That means a series of 4 combinations of zeros and ones, or 4 pairs of 2 bits each. That is 0, 0, 0, 1, 1, 0, 1, 1. I repeat, a group of 2 bits can be used to represent one of 4, that is 2 raised to 2 values. In other words, a group of 2 bits, that is 0 and 1 combination, can form 4 arrangements of zeros and ones. And those 4 combinations or pairs of 2 bits is 0, 0, 0, 1, 1, 0, 1, 1. These 4 values can represent 4 different symbols or characters. That is, from decimal digit 0 to 3. With 3 bits, we can have 8. That is 2 for the 2 states raised to power 3 bit patterns. For example, or that is 0, 0, 0, then 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0. I repeat, the arrangement of the 3 bits can be in the following order: 0, 0, 0. In fact, that is decimal digit 0. Then 0, 0, 1 for decimal digit 1. 0, 1, 0 for decimal digit 2. 0, 1, 1 for decimal digit 3. 1, 0, 0 for decimal digit 4. 1, 0, 1 for decimal digit 5. 1, 1, 0 for decimal digit 6. 1, 1, 1 for decimal digit 7. We are going to discuss in depth on how we arrive to this series of bits when we are going to be looking at number conversions, and attention being on decimal to binary number conversions. Therefore, look for my part 2 and part 3 of presentations in this series or in this topic and data representation from MLSwap ICT YouTube channel. This means we can now represent 8 different characters. That is 0 or character 0 to character 7 using 3 bits combinations or patterns. With the 4 bits, we can represent 16. That is 2 to power 4 characters. 2 for the 2 binary states, 0 or 1. 4 for the number of bits. So with the 4 bits, we can represent 16. That is 2 to power 4 characters ranging from decimal digit 0 to 15. Remember, 0 is also counted because it is a number in computing. It is a valid number. This is a significant number. And therefore, from decimal digit 0 to 15, we have 16 characters. And those can be represented with the 4-bit patterns of 4 bits. In other words, I repeat, with 16 characters, or to arrive at 16 characters, we can have 4-bit patterns composed of zeros and ones. While with 8 bits, we can represent 256, that is 2 raised to 8 characters, and so on. That is from decimal digit 0 to 255. My dear students and the rest of the learners, in fact, when I talk about 8 bits to forming 256 characters, I mean 8 bits, the first bit pattern will be a series of 0, 8 bits. 0, in other words, simply put, 8 bits forming 256 characters runs or spans from a series of 8 zeros, that is 0, 0, 0, 0, 0, 0, 0, 0. Those are 8 zeros. That represents digit 0. While the last bit pattern will be a series of 8 ones. That is 1, 1, 1, 1, 1, 1, 1, 1. And therefore, a series of 8 zeros forms decimal digit 0, while a pattern formed by a series of 8 ones forms decimal digit 255. Therefore, with n bits, we can be able to represent 2 raised to power n characters. 2 for the 2 states, on and off, while n is the number of bits. So you just need to replace n in your computation to be able to know the number of characters that can be formed using a certain number of binary digits. If the number of bits is, for example, 10, that means a series of bit patterns spanning from 10 zeros to 10 ones. Then, for you to be able to know the total number of characters that those 10 bits will be able to represent, you just need to pick 2 and raise it to the number of bits. For example, if the number of bits are 10, then you say 2 raised to 10. That is 2 to the power 10. And you get the respective number of characters. And therefore, with n bits, we can be able to represent 2 raised to 10 or 2 raised to n characters. That is from decimal digit 0 to n. Let's challenge our brains a little. Let's see whether you have understood what we have already learned. How many bits form your first name? How many binary digits form your first name? You have 1 minute to count them. Let's now see if you've been able to compute the number of bits for your first name. I'll use my example. This is how you proceed. First of all, write down your first name. My first name is Meme. Then the next step is count the number of characters that form your first name. My first name is composed of 5 characters. That is M, E, E, M, E, or E, E. Or you can simply say M, double E, M, E. Those are 5 characters. Then count the number of bytes that form your name. Remember, 1 character is equals to 1 byte. And therefore, 5 characters, which form my name, will be equals to how many bytes? What do? You multiply the number of characters with 1 byte divided by 1 character. In this case, for my case, it will be 5 characters times 1 byte divided by 1 character. The character and the character will cancel each other. And therefore, we shall be left with 5 bytes. However, we have already said that 1 byte is equals to 8 bits. So, how many bits will form or will be formed from our 5 bytes? Therefore, 5 bytes will be equals to how many bits? It is 5 bytes times 8 bits divided by 1 byte. The term byte and byte will cancel each other, and therefore we shall be left with 40 bits. And therefore, my first name, Meme, is composed of 40 bits. And therefore, my word length, the word length for my first name, Meme, is equals to 40 bits. Let's now focus on number systems and their representation of integral values. Number systems and their representation of integral values. Complex types of data, such as sound and pictures, take a lot of memory and processor time when coded in binary form. That's why higher number systems are used in computing to handle long streams of binary digits by reducing them into manageable form, thus improving the processing speed and optimizing memory usage. Therefore, the three main reasons why other number systems are preferred in representing data instead of binary system are: number one, binary system is cumbersome for humans to work with. And you have seen this from our tabulation for just the number of bits that form your first name. And therefore, you can imagine if you are dealing with volumes or pages of ones, that would be very cumbersome. Number two, complex data types take a lot of memory and the processor time when coded in binary digits. Number three, higher number systems reduce streams of binary into manageable form. So, the knowledge of number systems is essential because the design and organization of a computer is dependent upon the number systems. The knowledge of number systems is essential because the design and organization of a computer is dependent upon the number systems. Therefore, the number systems is a very important topic or area or field in computing that is important to be understood by every student dealing or handling issues to do with computers. Data can be represented in the computer using number systems or by using symbols, or what we call symbolic representation. The number systems can be classified into four major categories, which are decimal, normally represented as x base 10, binary, represented as x to base 2, or the number to base 2. So 2 illustrates binary. 10 illustrates that what you are dealing with is a decimal. We have octal, represented as x to base 8. 8 indicates that the number that you are dealing with is an octal. Hexadecimal, represented as x to base 16. 16 indicates that what you are handling or the number you are dealing with is an hexadecimal. The most common coding schemes used in symbolic representation of data, on the other hand, are 1. Binary coded decimal, BCD. 2. Extended binary coded decimal interchange code, EBCDIC. Number 3, American Standard Code for Information Interchange. American Standard Code for Information Interchange, ASCII. The number of bits used to represent a character is therefore determined by the coding scheme used. Let's look at number systems. We commence with decimal number system. D and S. This is a system of representing numbers with the use of 10 digits symbols 0 to 9 and combine the same digits to represent numbers that are greater than 9. So it's called base 10 number system or ordinary number system because it is composed of 10 digits spanning from digit 0 to 9, which may be represented as x to base 10. Decimal numbers have been used since time immemorial for counting because they naturally represent the 10 fingers of human beings. Talk of 10 fingers for the hand. Talk of 10 toes for the foot. Talk of 10 commandments, etc. The three parameters of defining the magnitude of a number in decimal number system are therefore, number 1, absolute value. This is the magnitude of a digit in a number according to its value in a number line. For example, the absolute value of digit 6 in the number 5649 is 6 because it is its possession in a number line. So if you have a number line from 0 to 9, then 6 will be the possession of digit 6 in the number line. So that is called absolute value for the number. The second one is place value. This is the possession of the digit in that number. For example, the place value of digit 6 in the number 5649 is a hundredths. Why? Because 6 in the number 5649, or that position of 6 represents 600. That's why if we were to read 5649 fully, it would be 5,649. So 6 represents the hundredths possession, and those hundreds are 6. So 600. That is 6 times 10 raised to power 2. 10 raised to power 2 is 100. So multiply by 6. Remember, 5 in terms of possession represents thousands. 6 is hundreds. 4 is tens. While 9 is ones. That's how we look, or we get, or we arrive at the possession of values of digits in a number. Then number 3 is base value. This is the radix or the subscript that indicates the type of number system that is being used. So in our case, we have 649 to base 10. In other ones, our number is 5649 to base 10. And therefore, 10 is the subscript. And so, our base value is 10. Why? Because 5649 is in decimal number system. Just as I have said, The base of the number indicates the number system that that number is in. For example, 5649 to base 10 simply means that that's a decimal number system because the numbers span from 0 to 10 or to 9, and those are 10 digits, so base 10. 8 indicates the base value is 8, meaning it is an octal. And that also means that the octal represents a series of 8 digits, 0 to 7. When we talk of 2 for binary, those are 2 numbers. So it's a series of 2 numbers, 0 to 1. If we talk of hexadecimal, then that would be base 16. 16 meaning that the numbers in that system span from digit 0 to 15. But of course, we are going to see how we represent numbers beyond digit 9 in hexadecimal system. The most important thing for you to note, my dear students, and the rest of the learners, is how we arrive at the base value. We always look at the subscript or the index for the number given. If it is 10, like it is our case for 5649, then we can be able to tell that that is a decimal number system. If the index or subscript is 16, that would be hexadecimal number system. If the index is 8, that is octal. If the index is 2, that is binary. The weight of each position is multiplied by the corresponding digit to obtain the value of that position. The values of each position are then added to obtain the total value of a number. For example, to get 5649, that is 5,649, the values of each digit position is calculated and added as follows. Remember, we are dealing with decimal number system, DEC for 10. So how do we compute? We begin with the list or the ones. In our computation, we begin dealing with the ones. That is what is on the digit on your rightmost part. 2 ones, the left. So we do the computation, the calculation, in this case, moving from ones to thousands, 100,000, etc. That is from your left-hand side to ones. That is from your right-hand side towards your left-hand side. So in this case, it is, and because our number 5649 is a decimal, we move as follows. 9 times 10 raised to power 0 plus next digit is tens, or represents place value of tens. So it is 4 times 10 raised to power 1 plus 6 times 10 raised to power 2 plus 5 times 10 raised to power 3. My dear students and the rest of the learners, whenever we are raising numbers, we begin raising with the 0. That is superscript 0, 1, 2, 3, etc. based on the length of the number or the number of characters forming our number. So in this case, we get 9 times 10 to the power 0 is 9 times 1. Then we have 4 times 10, because 10 raised to the power 1, or any number raised to the power 1 is that number. I repeat, any number raised to the power 0 is 1, or gives 1. Any number raised to the power 1 gives the same number. So 4 times 10. And then 10 raised to the power 2 is 100. That is 10 times 10. 100. So it is 6 times 100. Plus 5 times 1000. Because 10 raised to the power 3 simply means it is 10 times 10 times 10. 10 multiplying by itself 3 times, giving 1000. So the answer is 9 plus 40 plus 600 plus 5000, which gives 5649 to base 10 or index 10. Good. In any number, the rightmost digit has the least value and is called the least significant digit, LSD. In our case, it is 9. Or the leftmost digit has the most value and is called most significant digit, MSD. And in our case, it is 5. So you begin a computation from the least significant digit to the most significant digit. The value of each place increases by a factor of 10 for each consecutive digit moving from right to left. And my dear students and the rest of the learners, note that we are speaking of factor of 10 because we are dealing with decimal. If it was octal, it would be factor of 8. If it is binary, it is factor of 2. If it is hexadecimal, it is factor of 16. So the value of each place increases by a factor of 10 for each consecutive digit moving from right to left. My dear students and the rest of the learners, remember, we move from right to left of the number. Let's now test ourselves a little to see whether you have understood what we have done and said. Calculate the total value of 99999 index 10. Remember, each step matters. So you have 1 minute to execute this calculation. Let's see what you are supposed to do. So the solution is from the least significant digit, the most significant digit, we have 9 times 10 to power 0 plus 9 times 10 to power 1 plus 9 times 10 to power 2 plus 9 times 10 to power 3, and then 9 times 10 to power 4. Ten raised to 0 is 1. So we have 9 times 1 plus 10 raised to 1 is 10. So we have 9 times 10 plus 10 raised to 2 is 100. So we have 9 times 100. 10 raised to power 3 is 1000. So we have 9 times 1000. 10 raised to power 4 is 10,000. So we have 9 times 10,000. This gives us 9 times 1 is 9, plus 9 times 10 is 90, plus 9 times 100 is 900, plus 9 times 1000 is 9,000, plus 9 times 10,000, which is 90,000. The final answer becomes 99,999 to base 10. Let's now look at binary number systems, B and S. This is a system of representing characters in form of strings of bits, whereby a place value of a digit increases by factors of 2 from the right to left and base number 2. I repeat, this is a system of representing characters in the form of strings of bits, whereby a place value of a digit increases by factors of 2 from the right to left and base number is 2. This number system uses 2 digits, 1 and 0, to represent numbers. Binary numbers are therefore written with a subscript or index 2, that is x, to base 2. The binary number system is therefore similar to the decimal number system in that the position of a digit in a number determines its weight. The positional weights of a binary number are expressed as powers of 2, since 2 is the base of the binary system. In the case of decimal, as we have seen, we were expressing or computing the positional weight of the number by expressing it as power of 10. But for binary, we express our positional weights by power of 2. So 2 is the base of the binary system. For example, given the number 1101, the absolute value of the rightmost character 1 is 1, because it is its position in number line. Note that in decimal, our number line runs from 0 to 1. And therefore, the position of the rightmost character 1 will be its position in the number line, while its place or positional value will be that number multiplied by 2 to power 0. Remember, the least significant digit, the most right or the last character in a number which is normally the most or the least significant digit is computed, or its positional value is computed by raising the number to 0. If it is binary, we raise 2 to 0. If it is octal, we raise 8 to 0. If it is decimal, we raise 10 to 0. If it is hexadecimal, we raise 16 to 0. While the second least significant digit in that order will have its positional value computed by multiplying that number with the number which represents the number system, multiplied by or raised with 1, etc. So in this case, because we are computing the positional place value of 1, which is our least significant digit, in the number 1101, then we get that positional value as 1 times 2, which of course indicates binary, raised to 0, which gives 1 times 1. Because any number raised to power 0 gives 1. So it is 1 times 1, which is equals to 1. However, the place value of our most significant digit, which is 1 on the left-hand side, is 1 times 2 to power 3. Note, just as I have said, we raise our numbers with 0 from the least significant digit assigned or position. As we move towards the right or the leftmost, that is most significant digit, from 0 all the way. For example, in our number 1101, then to get the positional value of the least significant digit 1, it is 1 times 2, because it's binary, raised to 0. The positional value of 0 in that order, in that number, will be 0 times 2 raised to power 1. Then our next 1 in that order, as we move towards the most significant digit, will be 1, that is that number, times 2, represent the number system, raised to power 2. And lastly, the most significant digit in this case, which is 1, and it is our leftmost character, it will be 1, that is the number itself, times 2, driven from the number system, then raised to power 3. In other words, we raise numbers using the criteria 0, 1, 2, 3, 4, 5, 6, like that, based on the number of characters or the number of digits in our number, in the number we are dealing with. My dear students and the rest of the learners, you gain more understanding and deeper understanding as you proceed from this presentation, and then you visit MLE Swap ASCII YouTube channel for part 2 or 3 of this presentation, and then part 3 of 3 in this series. Therefore, the place value of our most significant digit 1 is 1 times 2 to the power 3. 2 to the power 3 means 2 multiplied by 2 multiplied by 2. That is 2 multiplied by itself 3 times. 2 times 1 is 2. 2 times 2 is 4. 2 times 2 times 2 is equals to 4 times 2, which is equals to 8. 1 times 8 gives 8. So the base value of 1101 is 2. Why? Because it is in binary number system. To the left of the binary number point, the weights are positive, while to the right of the binary point, the weights are normally negative. Each position in a binary number system is called a bit. The leftmost non-zero bit of any binary number is the most significant bit, and the rightmost bit, whether 0 or 1, is the least significant bit. Let's now pay our focus on octal number system, ONS. This is a system of representing characters consisting of 8 digits running from 0 to 7, where the place value of characters go up in factors of 8 from right to left, and base number is 8. The place value of 6, for example, in the following number, 5643, noting we are now referring to 5643 in octal, will be 8 raised to 2, or the place value of 3 will be 8 raised to 0. 5643 in octal simply indicates that 3 is the least significant digit in this number system, while 5 is the most significant digit. Where 5 is the most significant digit. And therefore, to get the place value of our least significant digit, which is 3, it simply means we shall multiply 8 with 8 raised to power 0. I repeat what I have already said. My dear students and the rest of the learners, you have already learned how to go about the binary number systems and the decimal number systems. So the formula of dealing with the octal number systems is similar to the one for the octal and to the one, that is to the one of decimal and to the one of binary. The only difference this time around is that now, wherever we are using 2 for the base, and wherever we are using 10 for the base, we are now replacing it with 8, because we are now dealing with an octal number system. And therefore, I have said that, for example, given the number 56 or 5643, 5643, to get the place value of any of those digits, you pick that digit, and then based on its possession, you raise that digit, and also you pick the base, which is 8, you raise it to the respective power based on the possession. So for 3, the place value will be 8 raised to 0. For 4, it will be 8 raised to 1. For 6, it will be 8 raised to 2. While for 5, it will be 8 raised to 3. So we move from the powers 0, 1, 2, 3, etc., moving from the least significant digit to the most significant digit in that order. That's why we are therefore saying that the place value of 6 in the number 5643 is 8 raised to 2, or the place value of 3, which is the least significant digit, is 8 raised to 0. Since binary numbers are long, and cumbersome, more convenient representations combining groups of 3 bits into octal, that is base 8 digits. The possession of a digit to the left of the octal point carries a weight in ascending powers of 8, just as I have already explained. Digits behind the octal points are used and are similar to decimal and binary points. Each digit of a number in base 8 has its place value determined by 8. For example, the place value of 6 in 5643 will be 64s, because it is 8 raised to power 2, while that of 3 is 1s, because it is 8 raised to 0, while that of 4 is 8s, because it is 8 raised to power 1. Let's now look at hexadecimal number system, HNS. This is a system of representing characters consisting of 16 digits ranging from 0 to 9 and A to F, where place values of each character goes up in factors of 16 and base number is 16. My dear students and the rest of the learners, kindly note that whereas we have said that an hexadecimal consists of 16 digits spanning from 0 to 15, the numbers below 9 are not represented as decimals. In other words, we don't write them as 10, 11, 12, 13, 14, and 15, but we replace any number beyond 9 with letter A to F. And therefore, our 16 digits range from 0 to 9 and A to F. That is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Therefore, 10 is represented as A, 11 as B, 12 as C, 13 as D, 14 as E, 15 as F. And therefore, A is equivalent to 10 and F is equivalent to 15 in base 10 system. This therefore informs you that 11 is equivalent to B, 12 is equivalent to C, 13 is equivalent to D, 14 is equivalent to E, and 15 is equivalent to F. Hexadecimal numbers are written with the subscript 16 as X to base 16. The place values of 6, for example, in the same example I've been giving, but now in base 16, that is 56 or 5648. My dear students and the rest of the learners, kindly listen to the way I am reading my numbers, except for the decimal where I read it as 5,648. For the octal, binary, and hexadecimal, I'm reading them in a different way. I am not saying 5,648 to base 16. No, I am saying 5648 to base 16. 5648 to base 16. Why? Because 5648 to base 16 is not equivalent to 5,648 in decimal. That is to base 10. Those are different numbers. Neither is it equal to 5648 in octal. So the place value of 6 in 5648 hexadecimal is 256. Why? Because it is 16 raised to power 2. For 8, it is 8, or it is 16 raised to 0. For 4, it is 16 raised to 1. For 6, it is 16 raised to 2. For 5, it is 16 raised to 3. The difference between the hexa in this case and the octal that we have dealt with is we are replacing 8 with 16. So the place value of 6 in 54 or in 5648 hexadecimal is 256 because it is 16 raised to 2, while place value of 8 is 1s because it is 16 raised to 0, which gives a 1. The hexadecimal system is popularly known as hex system. Each digit in base 16 has its place value expressed in terms of 16s. The main advantage of octal and hexadecimal numbers over decimal numbers is that they can be easily converted to and from binary numbers. Let's now look at what we call symbolic representations in data representation. In computing, a single character, such as a letter, a number, or a symbol, is represented by a group of bits. The number of bits per character depends on the coding scheme that is used. Various codes have been developed to represent data in the computer and to enable it to be easily transmitted between systems. Data that is represented in a computer is made up of characters which include number characters 0 to 9, alphabetic characters, that is lower case and uppercase letters. We have special characters and control characters such as backspace, delete, insert, etc. And all these characters need to be represented in the computer, not in using the normal binary, the normal octals, the normal hexadecimals, but using now a special or a set of special symbols, what we are calling special, or what we are calling symbolic representations. All the characters that a computer can store and process is called the character set of that computer. All the characters that a computer can store and process is called the character set of that computer. Each character is represented by a code consisting of either 7 or 8 bits called the character code. But the most common one is the 8 bits, which are equal to a byte. Coding is converting information, numeric or non-numeric, into binary form that the computer can understand. Therefore, coding is the process of converting numeric or non-numeric information in terms of binary digits. The most common coding schemes are BCD, EBCDIC, and ASCII. That is BCD, EBCDIC, and ASCII. Let's look at BCD. This is a 4-bit code used to represent numeric data only used in simple electronic devices to make it easier to process and display individual numbers on the LCD screens. In BCD representation, each digit of a number is represented as its 4-bit binary code. Then the bits are grouped together in their order as in the number being converted. For example, 5648 can be converted as 5 is equals to 0101. 6 is equals to 0101. 1, 0. 4 is equals to 0, 1, 0, 0. 8 is equals to 1, 0, 0, 0. Therefore, the BCD representation of 5648 will be 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0 to base 2. My dear students and the rest of the learners, for you to be able to know how we do number conversions from one number system to the next, kindly visit Emily Swap ICT YouTube channel and look and listen to part 2 and part 3 of my presentations on this topic on data representation in the computer. To represent a signed number, that is integer, which is with a positive or a negative sign, the most commonly used method represents positive as 1, 0, 1, 0. In other words, represents the addition sign or plus sign, that's a positive sign, as 1, 0, 1, 0, while the negative sign is represented as 1, 0, 1, 1. So if you have a number that commences with plus or minus, that is a dash negative or positive number, a number indicates whether, or a symbol that indicates whether the number is negative or positive, either addition sign or the subtraction or minus sign or negative sign, then we replace or we indicate the positive sign with 1, 0, 1, 0, and the negative sign with 1, 0, 1, 1. Therefore, to represent the number negative 5648, note, I am not saying minus 5648. I am reading it as negative 5648. It will be 1, 0, 1, 1. 1, 0, 1, 1 represents the negative sign. So it is 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0 to base 2. So to represent a decimal number in BCD, just replace each decimal digit with its equivalent for binary digit code. Although the number 10 through 15 could also be coded as 4-digit binary numbers, this is not done in BCD. The BCD code is not efficient because 6/16 of the available binary numbers are not used at all. However, number or conversion from binary to BCD is much simpler than converting from binary to decimal. BCD can be useful in applications where both output and input are decimal numbers and only a small amount of calculations will be done on the numbers. BCD codes are also useful for keyboards, inputs, and for displays. A standard or extended BCD is an enhanced format of BCD in which non-numeric characters are represented in form of 6 bits and allows representation of 64 characters. The additional 2 bits are called zone bits. An additional bit, known as parity bit, is also added. Parity bit can be a 1 or a 0 depending on the computer. Apart from BCD that can only represent decimal numbers, extended BCD can represent numerals, alphabets, and special characters in binary form. In extended BCD, the characters are classified into zones, which in turn are assigned zone bits. For example, zone 1 has characters A to 1 and is assigned zone bits 1, 1. Zone 2 is characters J to R, assigned 1, 0. And zone 3 is characters S to Z, assigned 0, 1. So if a number in extended BCD begins with or commences with 1, 1, then you can tell it is within zone A. If it commences with 1, 0, you can tell it is in zone B or zone 2. If it is represented as 0, 1, then you can tell that that is zone 3. And therefore, you can easily look at the binary representation of a character and tell whether it is in zone A or whether it is, that is A to the character preceding J. A, B, C, D, E, F, G, H, I. So zone A would span from A to I. Not A to 1, but A to I. I repeat. For example, zone 1 has characters A to I, not A to 1, as I had said before. It is A to I. So any character, so any number or any character represented with the first or most significant digits being 1, 1, that would indicate or would mean that that character is between or is within the range A to I. While any number represented in binary with most significant digits being 1, 0, that would indicate that that character is within the range J to R. While any that is indicated or commences with the most significant digits being or starting with the 0, 1, that would mean that that character is within the range S to Z. Counting starts from the first character within a zone and ends at the last character of the zone. For example, A is equal to numeric value 1, whose binary value is 0, 0, 0, 1. Therefore, the extended BCD of A will be 1, 1, 0, 0, 0, 1 to base 2, because it's in zone 1. Note, I have added 1, 1 on the most significant side. 1, 1, indicating that is in zone 1. B is equal to numeric value 2, whose binary value is 0, 0, 1, 0. Therefore, its extended BCD will be 1, 1, 0, 0, 1, 0 to base 2. J is in zone 2 and it's equal to numeric value 1, whose binary is 0, 0, 0, 1. So the first digit within a zone gets 0, 0, 0, 1. Therefore, its BCD is 1, 0, 0, 0, 0, 1. S is in zone 3, whose zone bits are 0, 1. And because it is the first in zone 3, and 1 is equal to 0, 0, 0, 1, then its extended BCD is 0, 1, indicating the zone. And because S is the first character within the zone, it gets 0, 0, 0, 1, which is normally equivalent to 1 in decimal. And therefore, the full number of the binary digits for S will be 0, 1, 0, 0, 0, 1. Now, I am talking about the first digit in zone 3 being S. In fact, the second one is T. So how would T be written? It is through the same. It's through the same. The zone is 0, 1. So we have 0, 1. And then because T is the second digit in that zone, second digit is equivalent to 2 in decimal. And the 2 is represented as 1, 0. Therefore, the decimal or the BCD for T will be 0 or 0, 1, 0, 0, 1, 0 to base 2. My dear students and the rest of the learners, in my presentation, I am giving you the hint on how to get the BCDs for the various numbers. What you need to note, or characters, what you need to note or bear in mind is which zone is the character. And that zone is represented by which binary values or numbers. And then what is the level of that number within the zone or that character in the zone? Is it number 1? Is it the first one? Is it the second one? Is it the third one? Is it the fourth one? Is it the fifth? If it is the fifth, get the decimal equivalent of 5 or binary equivalent of 5 in decimal. Then combine it with the 2 numbers that represent the zone. When you write it in the full, that will be the extended BCD for that character. So representing a given character in extended binary code therefore implies that the zone bits are added to the data bits and an extra parity bit is added. Let's now look at EBCDIC. EBCDIC. This is an 8-bit character coding scheme used primarily on IBM computers and can represent a total of 256 characters. It's an extension of the extended 6-bit BCD coding system. For example, A is represented as 11000001 to base 2. The 8th bit is used for parity checking. A parity bit is an extra bit which is added to a byte to ensure that the data received during transmission is exactly the one that was sent. This ensures data integrity. The two types of parity are therefore odd and even, and only one is used at a time. For example, if a computer is using even parity, a 1 or a 0 is added to the bit string to ensure that the number of ones in the bit string is always even. In an 8-bit byte, the leftmost bit would be changed to 0 or 1 to ensure that the number of ones is even. For example, if you want to transmit 11000001, a 1 can be added to make the number of ones even as 111000001 to base 2. Note, we are adding 1 on the most or towards the most significant side, the most significant bit. So we add 1 as the first bit on the most significant side. If the receiving device detects that the number of ones is odd, the data is rejected and an error is reported. The process is similar for odd parity, but done in the opposite way. Let's now look at ASCII. This is a 7-bit coding scheme that represents letters A to Z with binary digits similar to number 1 to 26. It can only represent 128 characters, that is 2 raised to power 7. Since computers can only understand numbers, all characters must be represented by a number. The ASCII numbers written in binary form. The 7-bit code is divided into 3 zone bits and 4 data bits, and an 8 bit added for parity checking. For example, character A can be represented with 8 bits as 11000001 because A is equals to ASCII code 65. And when you convert 65 decimal to binary, it gives you 11000001. So A is equivalent to 65 in decimal. When a document is in ASCII format, it means that the text is plain with no formatting. such as tabs, bold, or underline that any computer can understand. This makes it easy to import the file into other applications without issues of interpreting. Addition of the 8th bit makes ASCII to represent 256 characters. The 8th bit coding scheme is referred to as an 8-bit ASCII. ASCII code is mostly used in mini and PC computers, with EBCDIC mainly used in large IBM computing system. The first 32 character codes of ASCII are defined as control codes. A control code is a non-printable code that is used to tell the computer to carry out a command. This is done by assigning one of the control codes to a command. Control codes give the programmer the opportunity to assign commands to actions that they may want to personalize in a particular computer. To find out the ASCII code for a letter, you increase the codes by adding 1, that is binary digit 1, to the previous code. For example, if the ASCII code for letter A is 1000001, then the 7-bit ASCII code for B would be 100010, because 100001 plus 1 will give you 100010, according to the rules of binary addition that we are going to discuss in depth, or that I've discussed in depth in part 2 and part 3 of my presentations in this series that are already posted in MLSwap ICT YouTube channel. And for C would be 100011, because it is the ASCII code for B and then binary 1. While for G would be 100011. My dear students and the rest of the learners, for you to get deeper understanding about these additions and these representations, make sure you have listened to part 2 of 3 and part 3 of 3 of my presentations under this topic on data representation in the computer. An efficient method to find out ASCII code for a number, for example, G, would be to convert the binary code for A, that is 1000,001, to its decimal equivalent, that is 65. For B, it is 66. For C, 67. For D, 68. For E, 69. F, 70. G, 71. So once you have known the equivalent of A in terms of decimal, and you know it is 65, convert 65 decimal to its binary equivalent. And that will help you to be able to get the ASCII code for a character. Then find decimal equivalent for G, which is equal to 71. Then convert 71 to its binary equivalent to get the ASCII code for G. In other words, I'm simply saying that because you know that the equivalent of character A is 65, just count those numbers of decimals or decimal numbers from 65 upwards to represent, to be able to know the decimal number that is equivalent to the character that you want, or to the letter that you want to represent. If, for example, you want to get the equivalent, binary equivalent in ASCII for character G, for example, and you know A is 65. So just count from 65 to G. 65 equals to A, 66 to B, 67 to C, 68 to D, 69 to E, 70 to F, 71 to G. Then convert that 71 to its binary equivalent, and you'll be able to get the ASCII code for G, which in this case will be 1000111. Let's now test our brain a little. Represent meme, in other words, represent meme, which is my name, using ASCII code. Represent meme using ASCII code. How do we go about it? This is what to do. If A is equals to decimal equivalent of 65, then the decimal equivalent for E is 69 and M is 77. So you count from A being equal to 65, B 66, E 67, all the way. When you get the equivalent for E, that's 69, you note it down. And then equivalent of M is 77, note it down. Once you have noted them down, then get the decimal or binary equivalent. So the binary equivalent of E is 1000101. That is, you convert the decimal number 69 to its binary equivalent. And that binary equivalent will be equal to the ASCII letter that we want to represent, which is E. While for M is 77. Represented in its binary equivalent, which will be 1001101. My dear students, just as I've said, don't worry. Access my part 2 of 3 in this topic from Emily Swap ICT YouTube channel and part 3, and you'll be able to know how to convert one number system to another, including decimal that we are talking about, to its binary equivalent, and then to its equivalent ASCII character. Therefore, meme can be represented in ASCII as follows. M is equals to 1001101. The first E is equivalent to 1000101. The next E is equivalent to 1000101. Then or M is equivalent to 1001101. And the last E is equivalent to 1000101. And therefore, meme will be represented as follows in ASCII. 1 0 0 1 1 0 1 1 0 0 0 1 0 1 1 0 0 0 1 0 1 1 0 0 1 1 0 1 1 0 0 0 1 0 1. To base 2. I repeat, meme. That is the combination of those characters and arranged in that order. Starting with the first letter M to the last letter E, you represent it as, or you join those bits as follows. 1 0 0 1 1 0 1 1 0 0 0 1 0 1 1 0 0 0 1 0 1 1 0 0 1 1 0 1 1 0 0 0 1 0 1 in binary. Great. We have come to the end of part 1 of 3 of this presentation. You can now proceed to part 2 of 3 on the or under the title Data Representation in the Computer, part 2 of 3 with the title Number Systems Conversions. From part 2 of 3, or in part 2 of 3 of the presentation, you'll be able to know how to convert one number system to another. Congratulations for learning part 1 of 3 on the topic Data Representation in the Computer. You can access part 2 and part 3 of this topic, as well as other computer or ICT videos, by clicking or tapping on Emily Swap ICT YouTube channel below this video. You can also subscribe to this channel by tapping on subscribe button below this video if it's not currently reading as subscribed. You can also visit and subscribe to Emily Swap Life Skills YouTube channel for free life skills, motivational and inspirational resources. For any further correspondence, kindly write it to us through the email emilyswap@gmail.com. Thank you very much for listening to me, and be blessed.